So we've already seen how to explore the relationship between two variables, a dependent variable, in our case weight, and a single independent variable, width. But we often have more than one independent variable. So what we're interested in now is how do we combine multiple variables to try and explain what is going on with variation in our dependent variable. Just as an aside, I will also use the terminology throughout the course, response variable for our dependent variable, and covariate for the independent variables. That's the terminology I'll use most often. Unfortunately, you'll see a variety of terms used for those two different kinds of things. So looking at this graph, this shows us the distribution of weights of individuals by color. There were 4 color categories, but what we've done here is basically use the smallest category as the false and the lighter, higher categories as true. So higher numbers were lighter colors, and so that's what we'll look at here. We just split it into 2 groups. And these points indicate the medians. These whiskers indicate the max and min, or in the event that the maximum is more than 1.5 times the size of this box, then it shows it as a separate point. So we kind of get a sense of the distribution from these box plots, that perhaps light-colored individuals are heavier. But we also know that larger individuals are heavier. So what we really need to do is combine both of these things into a single model. So here's our scatter plot again. What we have now are circles for the dark-colored individuals and triangles for the light-colored individuals. If I fit 2 separate regression lines, one to the light-colored individuals and one to the dark-colored individuals, this is what I get. So there's a point at which the 2 lines cross. At higher, larger sizes, the light-colored individuals are, on average, a little bit heavier. But the reverse is true at smaller sizes, although there's not a lot of data down there. So this is effectively what we do when we do a multiple regression model, is we're going to combine these, what looks like 2 distinct regression lines, into a single model representation. And how we do that looks like this. So we still have our response or dependent variable over here on the left-hand side. There's going to be an intercept plus the effect, the rate of change in weight with increases in width. Then, so that part is more or less the same, although now this particular slope here represents what is going to happen, or what is the rate of change in weight for width when we are dealing with dark-colored individuals. The light-colored individuals then are coded as 0. So we have 0 for, or sorry, dark-colored individuals are coded as 0. So C times 0 gives us nothing. So this whole, and these 2 terms disappear. So this 2 over here says what's going to happen when we have dark-colored individuals. Then the C term here is basically saying how much does our intercept change when we're dealing with light individuals instead of dark ones. And the 4th term indicates by how much does the rate of change in width change, this term over here, when we're dealing with light-colored individuals. So this final term here is an interaction term. So light and width are interacting with each other so that the effect of width changes depending on what the variable light is. If we look at it, we fit those two models, we're going to end up with a table of estimates now. So previously we'd seen an intercept, and that's in the same sort of ballpark, keeping in mind that this is for a width of 0, okay, so it's not really a sensible sort of estimate. Here's the effect of width when light is false, that is when our animals are dark. Dark animals increase by 224 grams for every millimeter of carapace width. Our light-colored individuals, so now light is true, that's this third one here, minus 665. What does that mean? That means that when width is 0, remember, light-colored individuals are 665 grams lighter, that is more negative, than dark-colored individuals. Finally, we have this term down here, which is we can interpret as how does the effect of width change when we're looking at light-colored individuals. And so 26.21, that tells us that light-colored individuals, the increase in weight with increasing width is 26 grams greater per millimeter. So the slope for a light-colored individual would be 224 plus 26, or about 250. Now, so those are the four numbers that I've shown you before. We've actually got some new numbers here that we haven't talked about yet. Associated with each of these estimates is a standard error, which is just like it would be for a if we're calculating the standard deviation of a distribution. The standard error gives us a sense of how variable, or what is the spread of the distribution of our estimate now. And so 442, 17, 552, 21. These are all going to be positive numbers. By themselves, it's not really very easy to say what they mean. They really only become meaningful when you compare them with the estimate itself. So if we take the ratio of the estimate to the standard error, that's going to give us an indication of how far away from 0 our estimate really is in standardized terms, in units of standard errors. So this estimate is 7.8, nearly 7.9 standard errors away from 0. So if we were thinking of our distribution as a normal distribution, and if the mean was 0, this would be very, very far out on the margins of a normal distribution. So we're pretty confident that this estimate is not 0. And that's what this probability term here gives us, 3.94 times 10 to the negative 13. That would be the probability of getting an estimate this extreme or more extreme if the true intercept was 0. So when we look at width down here, we've got 224. The standard error is 17. That's 13 standard error units away from 0. So again, a very, very tiny probability that you would get an estimate this large or larger if the true effective width was 0. So this is evidence that, in fact, there is a relationship between width and weight, which not surprising given the graph, but this is sort of now some more statistical knowledge here. But let's look at these other two down here. So now we're looking at the effect of light. How much does it change the intercept? And the standard error is nearly the same magnitude as the estimate. So now we have a t-value that's only minus 1.2 standard errors, and it would not at all be unusual to get a value this large or larger if the true value of our effect here was in fact 0. So you have very little evidence that there's a change in the weight with change in light for light-colored individuals. And the same is true for the if the change in the slope, very close to 0 when measured in terms of our number of standard error units.